On December the 7th, 2025, the Sun and Earth spoke to each other, and the conversation was instantaneous. A solar flare erupted. 8 minutes later, its light reached us. But the earthquake in Alaska didn't wait 8 minutes. It didn't wait 8 hours. It happened in the same second. Zero delay. Zero lag. Something connected across 93 million miles of space, faster than physics says it should. While everyone's tracking 3i Atlas like it's the cosmic threat of the century, our own star just proved it can reach down and crack the planet beneath our feet. Scientists are scrambling. The data doesn't fit. And what's coming next, when that solar region rotates back around, might be far worse. Stay with me. Because what you're about to hear challenges everything we thought we knew about how planets break. You'll want to stick around as the Sun continues its dance with Earth, and the data keeps piling up. Subscribe and follow along, because every new discovery brings us closer to understanding what's really happening between our star and the ground beneath us. Now, let's settle in and unravel this solar mystery together. Picture this. December 7th, 2025. The Sun convulses. A massive solar flare rips from its surface, an M-class eruption so powerful that satellites on the day side of Earth register the electromagnetic pulse within 8 minutes. The X-rays slam into our upper atmosphere. Instruments light up. Solar physicists take note. And at that exact second, not hours later, not days later, but in the same breath, a magnitude 7.0 earthquake tears through the Alaskan crust. Same moment, same instant, zero delay. You're probably thinking, coincidence, random alignment. The universe is big, stuff happens, but here's where it gets uncomfortable. Some telemetry reports, admittedly from alternative data feeds, not your mainstream USGS bulletins, suggest the P-wave onset timestamp of that quake lines up with the solar flare detection down to the second. If that's accurate, we're not talking about correlation. We're talking about something that shouldn't be possible under the rules we've written for how planets work. Standard geophysics will tell you this. Solar flares can mess with satellites, fry electronics, create auroras. Sure. But shake the ground? No. The energy pathway doesn't exist. A coronal mass ejection, a CME, takes anywhere from 15 hours to several days to reach Earth. It has to cross 93 million miles of space, slam into our magnetosphere, and then maybe, if conditions are perfect, induce some currents in the ground. Telluric currents, they're called, but even those don't crack tectonic plates. They're whispers, not hammers. The crust doesn't listen to whispers. So what happened on December 7th? Let's build the scene. The hypothetical narrative floating around certain corners of the internet describes an M8.1 eruption. Before that, a smaller M1. 0.1 flare, a teaser, a warm-up. Then, the main event. The electromagnetic burst travels at light speed, so yes, it hits us fast. 8 minutes from photosphere to thermosphere. But electromagnetic radiation doesn't penetrate deep. It doesn't reach the mantle. It doesn't tickle fault lines. Physics says no. And yet, Alaska shook. Here's the thing about earthquakes. They're supposed to be independent events. Tectonic plates grind. Stress accumulates. Rock breaks. It's a mechanical process, not an electrical one. The timescales are geological. Decades. Centuries. Not seconds. Not synchronized with solar phenomena, 93 million miles away. But if the timestamp is real, if the alignment holds up under scrutiny, then we have a puzzle that doesn't fit into any textbook I've ever read. Some researchers, mostly outside the mainstream, but not all, are now asking a question that sounds absurd until you sit with it for a while. What if, under very rare conditions, there's a zero latency coupling between the Sun's electromagnetic output and crustal instability here on Earth? What if the Sun doesn't just threaten our technology, but our geology? Think about what that would mean. Every solar storm becomes a potential earthquake trigger. Every flare could set off a cascade. The ground beneath your feet, stable for millennia, suddenly responsive to something happening in the corona of a star. It's not the kind of threat you can see coming with a telescope pointed at the asteroid belt. It's not a comet. It's not a near-Earth object. It's the thing we orbit, the thing that gives us life, turning into a weapon. And while the world's attention has been glued to 3I Atlas, the interstellar visitor everyone's obsessing over, the mysterious object that might or might not be alien tech, depending on which YouTube rabbit hole you fall down, this threat emerges from our own star. Not from outside the solar system, from the center of it. What if we've been looking outward, scanning the dark for intruders, while the real danger was looming above us all along? Now let's be clear, the USGS doesn't buy this. Mainstream seismology doesn't accept the instant quake claim. There's no validated mechanism, no peer-reviewed paper establishing causation. The official position is that solar activity and earthquakes are unrelated phenomena. Full stop. And maybe they're right. Maybe this is all noise, pattern seeking and chaos, humans doing what humans do, finding connections where none exist. But the rest of this video is going to explore why some scientists, some researchers, some very smart people who don't wear tinfoil hats, are taking this seriously. Why the data, however controversial, however fringe, keeps pointing to something we don't understand. And why, if they're even partially correct, we might be facing a category of disaster we never planned for. Because here's the uncomfortable truth. We built our entire civilization on the assumption that the ground is stable, that earthquakes are local, mechanical events with no cosmic trigger. We mapped fault lines. We designed buildings. We created insurance models. All of it assumes the sun is irrelevant to seismology. If that assumption is wrong, even slightly wrong, then every hazard map is incomplete. Every prediction model is missing a variable. And every time the sun burps, we roll the dice. So where exactly did this quake hit? And why might that location matter more than you think? Because geography, it turns out, might be the key to understanding what happened and what could happen next. Imagine Earth as a sphere rotating through space, one half always facing the sun, the other half in shadow. On December 7th, when that M-class flare erupted, Alaska was squarely on the day side. Not just illuminated, positioned almost directly under the sub-solar point, or close enough that if any location on Earth could act as a receptor for solar electromagnetic energy, it was there. Geometry matters. If you're going to trigger something, you need line of sight. Alaska had it. Now, here's where the speculation gets interesting. Fault zones are fractures in the crust, places where tectonic plates meet and grind. They're also, at least according to some researchers, places where electromagnetic properties might differ from the surrounding rock. Water seeps into fault zones. Minerals align under stress. And some scientists, working on the fringes of mainstream geophysics, have proposed that under certain conditions, faults could act as something like antennas or amplifiers for electromagnetic disturbances. The idea goes like this. If a fault is already loaded with stress, already near the critical point where it's about to slip, then even a small perturbation, maybe a shift in telluric currents, maybe a pulse of electromagnetic energy, could be enough to push it over the edge. Not a direct transfer of energy, not the sun physically shaking the ground, but a trigger, a nudge. The fault was already cocked and ready to fire. It just needed the right signal. And here's the kicker. About 2 weeks before the December 7th quake, that same region experienced a magnitude 6.0 earthquake. Decent size, but not huge. You'd expect aftershocks. You'd expect a swarm of smaller quakes as stress redistributes. But that didn't happen. The fault went quiet. It locked up. Stress built, but it didn't release. Seismologists noted it. anomalous behavior. A fault that starts to break and then stops is like a door that swings halfway open and freezes. Something's holding it. Something's keeping it from finishing the job. So maybe, and this is pure hypothesis, that earlier quake was a failed release. The fault wanted to break, tried to break, but couldn't quite manage it. The stress remained. The clock kept ticking. And on December 7th, when the sun delivered its electromagnetic pulse, maybe that was the nudge, the whisper that became a scream. There's a concept in rock mechanics called the piezoelectric effect. Certain minerals, quartz for example, generate an electric charge when you squeeze them. The reverse is also true. Apply an electric field and the crystal deforms. Now, fault zones are full of crushed rock, water, minerals under immense pressure. If you could somehow inject an electromagnetic pulse into that system, could you alter the stress? Could you change the friction coefficient? Could you induce microfractures that cascade into a major rupture? Nobody knows. The research is thin. The experiments are hard to design. But the idea isn't completely insane. Some studies have looked at telluric currents and found localized anomalies before earthquakes. Whether those anomalies are precursors or just noise is still debated. But the fact that electricity and rock mechanics can interact, that's not controversial. The question is whether it can happen on a scale large enough to matter. Think about what a fault zone actually is. It's not just a clean break in solid rock. It's a zone of damage, sometimes hundreds of meters wide, filled with gouge, crushed, pulverized rock that's been ground to powder by millions of years of plate motion. This gouge is saturated with water in many cases. Groundwater percolates down, filling the pores, creating a fluid-filled channel that conducts electricity far better than dry rock. When you have water, dissolved minerals, and enormous pressure, you create an environment where electrical properties can shift dramatically. Some researchers have proposed that these fluid-filled fault zones act as natural waveguides for electromagnetic energy. When a pulse of energy enters the crust, whether from lightning, from industrial activity, or theoretically from solar-induced currents, it doesn't just dissipate randomly. It follows paths of least resistance. It channels through conductive zones. And fault zones, with their water and crushed minerals, are among the most conductive structures in the crust. Now, add stress to the equation. When rock is under enormous pressure, approaching the point of failure, its electrical properties change. Microcracks form and heal continuously. Charge accumulates at crack tips. The rock becomes electrically active. Some experiments have shown that stressed rock can generate electrical signals, precursory signals that appear before fracture. If incoming electromagnetic energy interacts with this already charged system, it's not impossible that it could tip the balance. It's not adding massive amounts of energy. It's adding the final straw, the last molecule of stress that breaks the camel's back. The USGS position remains clear. No convincing evidence links solar flares or magnetic storms to seismic events. They've looked at the data, they've run the correlations, and by their analysis, there's nothing there. Solar activity spikes, earthquakes happen, but the two aren't connected. It's random overlap. But here's the thing. In 2020, a paper published in Scientific Reports, a peer-reviewed journal, part of the Nature family, found something interesting. The researchers analyzed decades of data and discovered a statistical correlation between global proton density spikes in the solar wind and an increase in large earthquakes worldwide. Magnitude greater than 5.6. The lag time was about 1 day. Not instant, but close. The mechanism they proposed? Reverse piezoelectric effects in crustal fault zones. Solar wind compresses the magnetosphere, induces currents. Currents flow through the crust. Stress changes. Faults slip. Controversial? Absolutely. Widely accepted? No. But it's out there. in the literature, with numbers and error bars and statistical significance. It's not proof, but it's also not nothing. What makes this study different from earlier attempts to find solar earthquake links is the methodology. The researchers didn't just look at individual earthquakes and individual solar events. They looked at global patterns over decades. They used statistical techniques designed to filter out noise. They accounted for random chance. And after all that filtering, after all that statistical rigor, they still found a signal. A weak signal, yes. A signal that could be an artifact of the analysis, possibly. But a signal nonetheless. Other studies have failed to replicate these results. Some researchers have looked at the same data and found no correlation. Some have found weak correlations that vanish when you apply different statistical tests. This is how science works. Messy, contradictory, full of competing claims. But the fact that multiple independent groups are still publishing on this topic tells you it's not settled. The door isn't closed. The question remains open. If this hypothesis has even a grain of truth, then our entire approach to earthquake forecasting is missing a variable. We monitor tectonic stress. We track plate motion. We measure strain. But we don't factor in space weather. We don't include solar wind density or geomagnetic indices in our seismic hazard models. If faults under critical stress can be nudged by solar energy, then every forecast is incomplete. Every warning system has a blind spot. And here's the unsettling part. We can't see it coming. Tectonic earthquakes? We can at least map the faults, identify the high-risk zones, estimate return periods. But if the trigger is solar, if the nudge comes from above, then prediction becomes exponentially harder. You're not just monitoring the ground, you're monitoring the sun. And the sun doesn't care about our models. The sun operates on timescales that range from seconds to decades. Flares can erupt without warning. Active regions can intensify overnight. Magnetic field lines can twist into unstable configurations faster than we can measure them. Even with our satellites, our solar observatories, our sophisticated models, we're often surprised. We see a flare coming maybe hours in advance, sometimes less. A CME takes 15 hours to several days to reach Earth, which sounds like plenty of warning. But if you're trying to evacuate a coastal city or shut down a power grid in a coordinated way, it's not much time at all. And if earthquakes are part of the solar risk equation, if crustal failure can be triggered by space weather, then the warning time shrinks even further. Because faults don't wait. Once they start to slip, the rupture propagates at kilometers per second. You go from stable to catastrophic in the time it takes to draw a breath. So even if you knew a solar storm was incoming, even if you knew it might trigger a quake, what would you do? Issue an earthquake warning based on a solar forecast? Tell people to evacuate because the sun looks angry? Nobody would listen. Because it sounds absurd. Because it violates everything we've been taught about how planets work. And because the connection, if it exists at all, is probabilistic. Not every solar storm triggers a quake. Not every loaded fault slips when hit by a geomagnetic disturbance. It's a game of chance. A roll of the dice where the odds are low, but the stakes are catastrophic. So, what else happened on December 7th? Were there other signatures? Other clues? Because if this was a real coupling event, it wouldn't just show up in seismic data. It would show up everywhere. The Earth hums. You can't hear it, but it's there. The ionosphere and the surface form a cavity, and that cavity resonates at very low frequencies. The fundamental frequency is about 7.8 Hertz, called the Schumann resonance, named after the physicist who predicted it. It's always present, driven by lightning strikes around the world. Thousands of them, every second, creating a constant background electromagnetic hum. It's the planet's baseline. On December 7th, something changed. Community monitoring stations, hobbyist setups, some university labs, places like Tomsk in Russia that publish spectrograms online, recorded a broadband burst, energy spiking from near 0 Hz all the way up to 10 Hz, tapering off toward 25 Hz. It coincided with the solar flare and the Alaska quake. Not hours later. Right there, in the same window. Schumann resonances can shift. Lightning activity changes them. Geomagnetic storms can amplify them. But this was different. The energy profile didn't match typical thunderstorm signatures. And here's the thing. On December 7th, there was no reported global thunderstorm activity of the scale needed to produce that kind of spike. No massive convective systems. No tropical cyclones. Just a quiet day, meteorologically speaking. And yet, the cavity rang like a bell. So, what caused it? One hypothesis, and this is where we're firmly in speculative territory, is that the solar flare itself, or its interaction with Earth's magnetosphere, created a global electromagnetic disturbance, powerful enough to drive the Schumann resonance into overdrive. The ionosphere got hammered by X-rays and charged particles. The conductivity changed. The cavity's properties shifted. And maybe, just maybe, that disturbance propagated downward. Maybe it induced telluric currents deep in the crust. Maybe those currents reached fault zones. Maybe Alaska, already loaded with stress, felt the pulse and broke. It's a chain reaction. Space weather to atmosphere to ground. Each step amplified. Each step adding energy. Until something snaps. To understand why this matters, you need to understand what the Schumann resonance actually represents. The cavity between Earth's surface and the lower boundary of the ionosphere, about 60 kilometers up, acts as a waveguide for extremely low-frequency electromagnetic waves. When lightning strikes somewhere on the planet, it doesn't just create a local discharge. It sends electromagnetic waves propagating around the entire globe, trapped in this cavity. These waves circle the planet multiple times, interfering with each other, creating standing wave patterns at specific frequencies. 7.8 Hz is the fundamental mode. There are harmonics at roughly 14 Hz, 20 Hz, and so on. These resonances are always there, a constant planetary hum that's been the same for thousands of years, except when it's not. The amplitude of Schumann resonances varies with global lightning activity. More storms mean more strikes mean stronger resonances. This happens predictably. There's a daily cycle, because thunderstorms cluster in certain regions during certain times. There's even a seasonal variation. Scientists have been monitoring these patterns for decades. They know what normal looks like. And December 7th wasn't normal. The spectrograms show something unusual. Instead of the typical discrete peaks at 7.8, 14, and 20 Hz, the entire spectrum from 0 to 10 Hz lit up. It was a broadband burst. Energy spread across frequencies that normally don't carry much power. And it peaked right around the time of the solar flare and the earthquake. Some monitoring stations recorded the anomaly starting slightly before the quake. Some recorded it during, some after. The timing isn't perfect. These are hobbyist stations, not precision instruments synchronized to atomic clocks. But the pattern is there. What could create a broadband Schumann burst without corresponding lightning activity? One possibility is a sudden change in ionospheric conductivity. When a solar flare hits, the X-rays and extreme ultraviolet radiation ionize the upper atmosphere. More ionization means higher conductivity. The cavity between surface and ionosphere doesn't just change its dimensions, it changes its electrical properties. The resonance frequencies can shift. The quality factor can change. Energy can be injected into modes that normally aren't excited. People near the epicenter reported strange sensations. Low-frequency humming, not just during the quake, but afterward. For 24 hours, maybe longer. A vibration that didn't stop. Anecdotal, yes. Unverified, absolutely. But when multiple people in different locations report the same thing, you pay attention. Low-frequency vibrations are hard to ignore. They get into your bones. They feel wrong. Low-frequency sound, infrasound, below 20 Hz, has documented physiological effects. It can cause nausea, disorientation, a sense of dread. Some researchers have proposed that infrasound generated by geological processes might contribute to reports of haunted locations or paranormal experiences. The frequency range matches. 7 to 20 Hz is right in the zone where the human body resonates. Your chest cavity, your organs, even your eyeballs have resonant frequencies in this range. If Earth's electromagnetic field is oscillating at these frequencies, and if those oscillations somehow couple to atmospheric pressure waves or ground vibrations, then people would feel it. They wouldn't know what they were feeling, but they'd know something was wrong. There's an idea, mostly fringe, mostly dismissed by mainstream science, that Earth can be overdriven into resonance. That under the right conditions, an external energy source can push the planet's electromagnetic systems past their normal operating range. Think of it like hitting a tuning fork too hard. It rings louder, longer, at frequencies it normally wouldn't reach. The crust vibrates. Fault zones feel the stress. And if one is already on the edge, it breaks. The planet as a bell. The sun as the hammer. The physics of this is tricky. Electromagnetic waves in the Schumann resonance range don't penetrate deeply into the crust. They're essentially trapped in the atmosphere, but they can induce currents at the surface. Telluric currents, electrical currents flowing through the ground, following paths of high conductivity like ore bodies, aquifers, fault zones. These currents are well documented. Power companies monitor them because they can induce voltages in long transmission lines. During geomagnetic storms, telluric currents can get strong enough to trip circuit breakers, damage transformers. But can they affect fault zones? Can a current flowing through the crust change the stress state enough to trigger an earthquake? Most geophysicists would say no. The energy is too small. The coupling is too weak. But some would say, maybe. If the fault is already at the critical point, already microseconds away from failure, then even a tiny perturbation might be enough. Not adding energy to break the rock, but adding information, a signal that propagates through the stressed system, triggering a cascade of micro-failures that coalesce into a major rupture. The USGS and other leading geoscience organizations maintain that there's no convincing evidence of electromagnetic precursors or triggers for earthquakes. They've studied pre-quake anomalies for decades. Sometimes people report weird lights, magnetic disturbances, animal behavior changes. But when you run the statistics, when you account for confirmation bias and the sheer number of earthquakes that don't have precursors, the signal vanishes. It's noise, pattern seeking in chaos, and they have a point. The history of earthquake prediction is littered with failed claims. People who saw patterns that weren't there, correlations that didn't replicate, mechanisms that sounded plausible but didn't hold up under scrutiny. The scientific community has learned to be skeptical because the cost of false alarms is high and the benefit of genuine prediction has remained frustratingly out of reach. But some fault zone studies, localized, small scale, often published in open access journals that don't get much mainstream attention, have found correlations. Shallow earthquakes increasing after geomagnetic storms. Microquake swarms linked to sudden shifts in local magnetic field intensity. The results aren't universal. Many studies find nothing, but a few find something, and that something refuses to go away. One study from Japan looked at earthquake activity in a specific region over several solar cycles and found that seismicity increased slightly during periods of high geomagnetic activity. The effect was small, barely above the noise threshold, but it was statistically significant. Another study from Turkey examined shallow crustal earthquakes and found a weak correlation with certain solar wind parameters. Again, small effect, but reproducible. These aren't mainstream results. They haven't revolutionized seismology, but they're published, peer-reviewed, and they keep appearing. Why does this hypothesis persist? Because it's tantalizing. Because it suggests that we're missing a piece of the puzzle. Because if it's true, even partially true, it means earthquakes aren't purely tectonic. They're also cosmic, and that changes everything. Think about what it would mean for hazard assessment. Right now, we estimate earthquake probabilities based on fault slip rates, historical seismicity, geodetic measurements of crustal deformation. We build probability maps. This region has a 30% chance of a magnitude 7 earthquake in the next 30 years. But if solar activity is a factor, even a minor one, then those probabilities aren't constant. They vary with the solar cycle. They spike during geomagnetic storms. A fault that's safe 99.9% of the time might become dangerous during that 0.1% when the sun is active and conditions align. A ghostly hum over the planet, invisible but powerful. Maybe enough to shake the ground beneath our feet. Maybe enough to crack a fault that was waiting, just waiting, for the right frequency. But here's the question nobody wants to ask. What if December 7th wasn't a one-time event? What if the solar region responsible for that flare is still active, still building energy? What if it's about to come back around, stronger than before? Because the sun rotates, active regions move, and when they disappear over the limb, we lose sight of them. For about 25 days, they're on the far side, hidden, evolving. And when they return, sometimes they're monsters. The sun rotates once every 27 days, give or take. That means any active region, any cluster of sunspots, any pocket of twisted magnetic field spends about 2 weeks facing Earth and 2 weeks on the far side, out of view. We can't see it. We can't monitor it. All we can do is wait for it to come back around and hope it hasn't gotten worse. In the hypothetical narrative circulating among some solar physicists and space weather enthusiasts, the sunspot group responsible for the December 7th flare rotated out of view shortly after the event. It's over there now, on the far side, brewing. And the concern, speculative, but grounded in real solar physics, is that far-side evolution can intensify magnetic complexity. The field lines twist, shear, reconnect, energy builds. And when that region rotates back into view, it might not be an M-class flare anymore. It might be X-class, or worse. History offers precedents. Active regions that seemed moderate on their first rotation sometimes return as powerhouses. Sunspot groups that produced small flares on one pass come back and unleash storms. It's not predictable. Solar physics is chaotic, but it happens often enough that solar forecasters watch these rotations carefully. They know that the far side is a black box, and black boxes can hide monsters. The problem with far-side monitoring is that we have very limited tools. There are helioseismic techniques, measuring acoustic waves that propagate through the sun's interior and emerge on our side, that can give us rough indications of large active regions on the far side. But the resolution is poor. We can detect that something is there, but we can't see its structure, can't measure its magnetic complexity, can't predict what it will do. It's like trying to diagnose a patient by listening to echoes through a wall. You might hear a heartbeat, but you're missing everything else. NASA's stereo satellites used to give us a direct view of the far side. Launched in 2006, they orbited the sun at different speeds than Earth, providing stereoscopic views that let us see active regions before they rotated into Earth view. But contact with one of the stereo spacecraft was lost for years, and while it was eventually recovered, the mission is aging. We don't have comprehensive far-side coverage anymore. We're partly blind, and that's unsettling when you're trying to forecast space weather that could, hypothetically, trigger geological disasters. So let's play out the scenario. The sunspot region rotates back around. It's stronger now. The magnetic field is more twisted, more unstable. Earth is in its sights again, and let's say, purely for the sake of exploring the edge case, that our magnetosphere is already compressed. Maybe it's seasonal. Maybe it's a geomagnetic storm from another CME. Maybe we're just unlucky. The shielding is down. The magnetic field lines are stretched thin. Now the flare hits. But this time it's not an M class. It's X class. Maybe X5. Maybe higher. The electromagnetic pulse is orders of magnitude stronger. It slams into the magnetosphere, induces massive currents in the ionosphere, sends telluric currents surging through the crust. And if there's a fault zone under critical stress, anywhere on the planet it might slip. Not just Alaska, not just one location. Multiple faults, multiple quakes, a cascade. The X-ray classification system for solar flares is logarithmic. Each letter represents a tenfold increase in peak X-ray flux. An M-class flare is 10 times stronger than a C-class. An X-class is 10 times stronger than M-class. And within each class, there are numerical subdivisions. An M5 is 5 times stronger than an M1. An X10 is 10 times stronger than an X1. So when you go from an M8 to an X5, you're not talking about a small increase. You're talking about something 6 or 7 times more powerful. The energy difference is enormous. What does that energy do? In the traditional view, it heats the ionosphere, creates additional ionization, disrupts radio communications, maybe damages satellites if they're unlucky. But if there's a coupling mechanism between the ionosphere and the crust, if telluric currents can be induced at sufficient strength to affect fault stability, then an X-class flare doesn't just threaten technology. It threatens geology. This is the nightmare scenario, the perfect storm. Solar activity, magnetospheric compression, and tectonic stress all aligning. It's a low probability event, extremely low. But low probability isn't zero probability. And when the consequences are catastrophic, you pay attention to the tails of the distribution. Risk assessment in complex systems is tricky. You can calculate probabilities for individual events, probability of a magnitude 7 earthquake in California, probability of an X-class flare during solar maximum. But when you start combining events, when you look at conjunctions, the math gets complicated. If each event is independent, you multiply the probabilities, and the joint probability becomes vanishingly small. But what if they're not independent? What if solar activity actually influences seismic activity? Then the probabilities don't multiply. They correlate, and correlated risks are far more dangerous than independent ones. Solar physicists will tell you, privately at least, that the big worry isn't the flares we see coming. It's the ones we don't. The far-side eruptions that develop quickly, rotate into view, and hit us before we can react. 15-hour warning for a CME sounds like a lot, but if the magnetic field is oriented perfectly, if the coupling is optimal, if everything goes wrong at once, 15 hours might not be enough. 15 hours to shut down vulnerable satellites, to alert power grid operators, to prepare hospitals and emergency services. It sounds manageable until you account for bureaucracy, communication delays, the sheer inertia of large systems. And if you need to add earthquake preparation to that list, identifying vulnerable faults, evacuating populations, mobilizing response teams, 15 hours becomes laughably inadequate. And here's the thing. Even moderate geomagnetic storms, G3, G4, can disrupt power grids. Transformers fail. Satellites glitch. Communications go dark. We've seen it before. The Quebec blackout in 1989 was caused by a solar storm. The Carrington event in 1859 fried telegraph systems worldwide. If something like that happened today, with our modern dependence on technology, the economic damage would be in the trillions. The Quebec blackout is worth examining in detail because it illustrates how vulnerable our infrastructure is. On March 13th, 1989, a CME hit Earth's magnetosphere. The geomagnetic storm that followed induced currents in Quebec's power grid strong enough to trip circuit breakers and damage transformers. 6 million people lost power in 90 seconds. The blackout lasted 9 hours. Repairs took weeks. And that was from a storm that, while severe, wasn't anywhere near Carrington event levels. The Carrington event is the gold standard for worst-case solar storms. In September 1859, a massive CME hit Earth. Auroras were visible at tropical latitudes. Telegraph systems worldwide went haywire. Operators reported sparks flying from equipment, paper catching fire. Some systems continuing to operate even after being disconnected from batteries, powered purely by induced currents. If something like that happened today, estimates suggest it could cause up to $2 trillion in damage to global infrastructure and take years to fully repair. But if the event is stronger, if it's combined with worst-case coupling to the crust, the result could go beyond technological. It could be geological. Earthquakes, volcanic activity, crustal instability on a scale we've never observed in recorded history. Volcanic activity is another potential concern. Volcanoes, like faults, are complex systems operating near critical thresholds. Magma chambers sit beneath the crust, pressurized, waiting. The trigger for eruption can be subtle, a small earthquake that cracks the rock above, a change in stress that allows gas to exsolve and drive explosive decompression. If electromagnetic disturbances can affect fault zones, can they affect volcanic systems? The research is even thinner here than for earthquakes, but the question is worth asking. A major volcanic eruption triggered by solar activity would be catastrophic not just locally, but globally, potentially injecting enough ash into the stratosphere to affect climate. Nobody's saying this is likely. Nobody's claiming it's imminent. But the possibility exists. And the fact that it exists means we should be watching. We should be monitoring not just space weather, but also how it interacts with the ground. We should be asking whether our seismic hazard models are complete. The clock is reset. The hidden beast is reloading. And in roughly 3 to 4 weeks, the sun may point that beast right at us. But let's take a detour. Let's step into even stranger territory. Because some people, researchers, enthusiasts, conspiracy theorists, take your pick, believe that Earth itself isn't just a passive victim. They believe the planet has built-in nodes, resonant points, places where cosmic energy couples more efficiently. And they believe ancient civilizations knew about them. There's a theory that won't die. You've probably heard versions of it. The idea that the pyramids of Giza, the Nazca Lines, Angkor Wat, Stonehenge, and dozens of other ancient megalithic sites aren't randomly placed. That they're positioned on a global grid, a network of nodes aligned with Earth's natural harmonic resonances. That these sites were built not just for ceremony or astronomy, but as markers, amplifiers, or stabilizers of planetary energy. Fringe science? Absolutely. Dismissed by mainstream archaeologists and geophysicists? You bet. But the idea persists because the geometry is tantalizing. Draw lines between these sites, and sometimes you get patterns. Equidistant spacing, alignments with magnetic field lines, ratios that match the golden ratio, or pi, or other constants. Coincidence? Probably. But humans love patterns. And when the patterns are pretty, they're hard to ignore. Now let's add a twist. The December 7th Alaska quake, its epicenter, is allegedly, according to some geometric analyses floating around online, roughly equidistant from several of these ancient sites. Not perfectly, not with laser precision, but close enough that people noticed, close enough that the claims started spreading, And if you buy into the grid hypothesis, that makes the Alaska epicenter a node, a resonant point, a place where cosmic energy and planetary structure intersect. The argument goes like this. Earth is a giant resonant instrument. It has natural frequencies, standing waves in the crust, harmonic modes that can be excited by external energy. Strike the right node with enough power, say, a massive electromagnetic pulse from the sun, and the planet rings. Energy propagates through the crust. Fault lines, being zones of weakness, absorb the stress and release it as earthquakes. It's a beautiful idea. Almost poetic. The planet as a bell, ancient sites as the nodes, the sun as the striker. But is there any evidence, any data to support it? Short answer, no. Not in the way mainstream science requires evidence. No peer-reviewed studies validating the grid. No geophysical models incorporating ancient sites as resonant nodes. No reproducible experiments showing that megalithic structures affect seismic activity. But that doesn't stop people from pointing to anomalies. The ELF and ULF spikes recorded before some major earthquakes, extra low frequency and ultra-low frequency electromagnetic signals that some researchers claim are precursors. The Mexico earthquake in 2017, the Sumatra quake in 2004. In both cases, there were reports, mostly anecdotal, mostly unverified, of unusual electromagnetic activity before the main event. Satellites detected magnetic anomalies. Ground-based sensors picked up low-frequency hums. Mainstream scientists say these are artifacts, sensor noise, or post-hoc pattern seeking. The problem with precursors is that you never know they were precursors until after the earthquake happens. It's easy to look back and say, see, there was a signal. But if you can't predict the next quake using those signals, what good are they? Still, the hypothesis survives. Why? Because it gives meaning to chaos. Earthquakes are terrifying precisely because they're random. No warning, no pattern. The ground just breaks. But if there's a grid, if there's a cosmic trigger, if ancient civilizations knew something we don't, then maybe it's not random. Maybe it's a system we can understand. Maybe, just maybe, we can predict it. And there's something psychologically comforting about that. Even if the system is sinister, even if the sun is weaponized, even if ancient sites are amplifiers of disaster, at least it's a system. Humans can deal with systems. We can't deal with pure randomness. But let's be honest. Mixing fringe theories with real scientific data is dangerous. It blurs the line between speculation and fact. It makes people believe things that aren't true. And when disaster strikes, when people are looking for answers, bad information can be as deadly as the quake itself. So here's the ethical warning. Take all of this with a massive grain of salt. The grid hypothesis isn't validated. The ancient site alignment is cherry-picked. The electromagnetic anomalies are controversial at best. But the core question, can the sun influence Earth's geology? That's still worth asking. Even if the answer involves no ancient mysteries, no cosmic nodes, just boring old plasma physics and rock mechanics. Could our ancestors have known something we don't? Maybe. Or maybe they were just really good at picking dramatic locations for their monuments. Either way, we're stuck in the present, trying to make sense of data that doesn't fit the models. And speaking of data, 2025 has delivered some scientific developments that feel straight out of a science fiction novel. Quantum anomalies, planetary surprises, biological weirdness. The world of science keeps churning, and some of what it's churning out might actually shift our understanding of Earth's vulnerability. While we debate solar quake coupling and ancient grids, the world of science keeps moving. And 2025 has been a year of surprises, not all of them comforting, some of them downright unsettling. Let's zoom out and look at what else is happening, because context matters. Because the more we learn about Earth, about the sun, about how interconnected everything is, the less stable things seem. Start with the solar wind correlation. Remember that 2020 study from Scientific Reports? The one that found a statistical link between solar wind proton density and large earthquakes? Well, there's been follow-up. Not a smoking gun, not definitive proof, but enough that researchers are still poking at it. Some groups have expanded the dataset, included more seismic events, refined the statistical methods, and the correlation persists. It's weak, it's noisy, but it's there. The significance isn't that we've proven causation. We haven't. The significance is that mainstream researchers, people with PhDs, people publishing in respectable journals, are still actively exploring this. They're not laughing it off. They're treating it as a legitimate, if controversial, avenue of inquiry. That tells you something. It tells you the boundaries of what we know are softer than we'd like to admit. Then there's the magnetoreception stuff. Humans have always assumed we're insensitive to magnetic fields. Birds can sense them. Turtles navigate with them. But us? No way. Except recent studies, some from just this year, suggest otherwise. Certain proteins in the human eye, cryptochromes, might respond to magnetic fields. We might have a latent sense we never knew existed. It's not strong. It's not like we can navigate by compass. But it's there. Why does that matter? Because if biological systems can detect and respond to subtle geomagnetic changes, then what else are we missing? What other invisible forces are shaping life, behavior, physiology? And if life is sensitive to these fields, then maybe the crust is too. Maybe everything is more connected than we thought. There's also the cosmic ray angle. Cosmic rays, high-energy particles from deep space, constantly bombard Earth. The magnetosphere deflects most of them, but some get through. And recent research has suggested that cosmic rays might influence cloud formation, weather patterns, maybe even climate over long timescales. The mechanism is still debated. The evidence is still shaky. But if it's real, it means that events happening light years away, supernovae, gamma ray bursts, could shape conditions on Earth. Connect the dots. Solar wind affects the magnetosphere. The magnetosphere shields us from cosmic rays. Cosmic rays might affect the atmosphere. The atmosphere interacts with the crust through pressure, temperature, ionospheric coupling. Everything feeds back into everything else. It's not a linear system. It's a web, and webs can have unexpected failure modes. Imagine a scenario. The sun erupts. The magnetosphere compresses. Cosmic ray flux increases. Ionospheric currents surge. Telluric currents spike. A fault slips. The quake releases radon from the crust. Atmospheric chemistry changes. Cloud patterns shift. More cosmic rays penetrate. The loop continues. Each step amplifies the next. Until something breaks. Is this happening? We don't know. Could it happen? Maybe. The more we study Earth as a coupled system, crust, mantle, oceans, atmosphere, ionosphere, magnetosphere, the more we realize how many variables we've ignored. We've treated each domain as separate, isolated, independent, but they're not. They're all talking to each other, and sometimes, rarely, the conversation gets loud. The central thesis here is that catastrophic events might not always need the obvious triggers. No asteroid collision, no supervolcano, no tectonic megathrust. Sometimes, maybe, a quiet resonant trigger from above is enough. A solar flare hitting at the wrong moment, with the wrong geometry, on a fault that's already loaded. And the planet cracks. The more we look, the less stable things seem. Every new study reveals another coupling mechanism, another feedback loop, another way for energy to propagate through the system. And every time we think we've mapped all the hazards, something surprises us. What if future research reveals thresholds? Specific combinations of solar wind density, electromagnetic flux, geomagnetic field strength, crustal stress, and alignment geometry that, when met, trigger chain reactions. What if we can identify these thresholds, monitor them in real time, and issue warnings? Or what if we can't? What if the system is too chaotic, too nonlinear, too sensitive to initial conditions? What if the next great disaster comes from a direction we're not even watching? These are hypotheticals, speculations, thought experiments, but they're not absurd. They're grounded in real physics, real data, real questions that scientists are asking. And the fact that we're asking them means we don't have the answers yet. We're still learning, still discovering, still finding out just how much we don't know. Which brings us to the cutting edge. The tools we're building right now, AI, advanced plasma modeling, satellite networks, that might finally give us the ability to see these threats coming, or at least understand them when they hit. Step back, take a breath. We've covered a lot. Solar flares and earthquakes synchronized to the second. Fault zones acting as antennas. Schumann resonances spiking without lightning. Far-side threats rotating back into view. Ancient grids and cosmic nodes. Biological magnetoreception and atmospheric coupling. It's a lot. It's overwhelming. And the question you're probably asking is, what do we do with all this? How do we make sense of it? How do we prepare? The answer might lie in technology, specifically in the convergence of artificial intelligence and plasma physics, because in 2025, we're on the edge of a revolution. New AI-based models are being developed or are already deployed that can predict solar flares with unprecedented accuracy. Not just there's a 50% chance of a flare in the next 48 hours, but specific timing, intensity, trajectory, machine learning trained on decades of solar data, learning patterns humans can't see, detecting signatures buried in noise. These models might soon be able to identify invisible threats, complex magnetic reconnection events, far-side activity inferred from helioseismic data, plasma density anomalies that precede major eruptions. And if we can predict the solar side of the equation with high confidence, then we can at least watch for the Earth side. We can monitor fault zones during high-risk periods. We can deploy extra sensors. We can issue warnings. But it's not just about prediction. It's about detection. Low Earth orbit satellites are constantly collecting data. Accelerometers, magnetometers, plasma probes. And recently, again, this is speculative, based on rumors and unverified reports, there have been hints of unexpected anomalies. Subtle magnetic fluctuations that don't match the models. Sub-threshold disturbances that shouldn't be there. Maybe it's instrumental noise. Maybe it's the environment changing. Or maybe Earth's magnetic shielding is shifting in ways we haven't noticed yet. And if the shield is weakening, even slightly, then the coupling between solar plasma and the crust could be getting stronger. We need expanded global monitoring. Magnetometers everywhere, not just at a few research stations. Ionospheric sensors blanketing the globe. Schumann resonance networks in real time, publicly accessible. Crustal stress sensors near major fault zones. All of it feeding into a centralized AI system that can detect patterns, correlations, anomalies. Not to predict individual earthquakes, that might still be impossible, but to flag high-risk periods. To say, the sun is active, the magnetosphere is compressed, this fault is loaded, watch closely. Would it work? Maybe, maybe not. But it's better than what we have now, which is basically nothing. We monitor space weather for satellites and power grids. We monitor earthquakes after they happen, but we don't integrate the two. We don't look for the coupling. And if the December 7th event was real, if the synchronization was causal, then that's a massive oversight. Here's the philosophical closing thought. Humans have always assumed Earth's geology is independent. The ground moves because of plate tectonics, because of mantle convection, because of processes happening inside the planet. The sun, irrelevant. It's 93 million miles away. It gives us light and heat, but it doesn't touch the crust. Except, maybe it does. Maybe our planet is far more dynamic, far more responsive, far more fragile than we've been willing to admit. Maybe the stability we've enjoyed for the past few thousand years, the quiet seismic periods, the predictable patterns, maybe that's the anomaly. Maybe Earth's normal state is more chaotic, and maybe the sun, our life-giving star, is also a chaos generator, a wild card, a source of unpredictability that we've been ignoring because it didn't fit our models. If the sun can yank the tectonic rug from under our feet, what does that mean for life, for civilization, for our long-term survival? How many disasters have we already misattributed to natural tectonic causes when the real culprit was cosmic? How many ancient collapses? How many lost cities? How many mass migrations were triggered not by drought or war, but by the sun deciding to hiccup at the wrong moment? We don't know. And that's the terrifying part. We don't know because we haven't been looking. We've been focused on the ground, on the plates, on the faults. We've been measuring strain and slip and recurrence intervals. But we haven't been looking up. We haven't been asking whether the star we orbit might also be pulling the strings. None of this is proven. The instant flare-quake coupling remains unverified. The mechanisms are speculative. The grid hypothesis is fringe. The statistical correlations are weak and controversial. But the act of asking the question, the act of shining a light on the unknown, might be our only chance to spot the next real threat before it hits. Because here's the thing about catastrophes. They don't announce themselves. They don't give press conferences. They just happen. And afterward, we pick through the rubble and try to figure out what went wrong. But what if for once we could see it coming? What if we could connect the dots before the disaster instead of after? What if we could say, the sun is active, the magnetosphere is weak, this fault is loaded, evacuate now? That's the goal. That's the dream. Whether we get there depends on whether we take these questions seriously. Whether we fund the research, whether we build the monitoring networks, whether we integrate space weather and geophysics into a unified framework. It's not sexy. It's not the kind of thing that gets headlines. But it might save lives. It might save civilization. So while the world obsesses over 3i Atlas, while we scan the skies for interstellar visitors and rogue asteroids, maybe we should also keep one eye on the sun. Because the sun is right there. 93 million miles is nothing on a cosmic scale. It's our neighbor, our parent, and maybe, just maybe, our greatest threat. The ground beneath your feet isn't as solid as you think, and the star above your head isn't as benign as it seems. Welcome to the solar-Earth coupling nightmare. Welcome to the possibility that we've been living on borrowed time. Welcome to the edge of understanding, where physics meets mystery, and the only certainty is uncertainty. Sweet dreams.